Now, whenever you can use Gibbs sampling, you should. The only challenge is, of course, is that it's sometimes difficult to be able to implement a Gibbs sampling scheme. And oftentimes people have to resort to sort of the brute force Metropolis Hastings that we've previously seen. But Gibbs sampling is in general very useful, and it is used exclusively for sampling from multidimensional distributions. Obviously, we'll be focusing a little bit on multidimensional posteriors in our future examples, but in any case, the key here is that the distributions need to be multidimensional. So we think of sort of having many variables, let's call them 1 to m, from which we sample from. And we already know that this is a vector of R1 all the way to Rm. And if we write something like this, we understand it to mean Rm all the way to big Rm. The notation I'd like to introduce here, as we talk about Gibbs sampling, is R minus m, which is R1 all the way to Rm minus 1, Rm plus 1, ... all the way to Rm. So if we think about what this means, this minus m means, it simply implies that we are missing the R sub m variable. So in Gibbs sampling, it'll be very convenient to talk about Rm as well as R minus m. In other words, the collection of variables that exclude the mth variable. So an object that'll pop up very often is sampling Rm conditioned on everything else, which is sampled from some distribution, superscript m, conditioned on R minus m. So this is the distribution for the mth variable, conditioning or with parameters R minus m. And of course, just to be concrete, this, the coinciding density, is equal to P of Rm conditioned on R minus m. So we'll be using this notation here in order to be able to designate the fact that we are conditioning on everything but the mth variable. So Gibbs sampling is actually pretty straightforward to explain. As a simple example, and then we can talk about why it works. So let's consider some R 1 to 2, and the goal is to sample some distribution P of R 1 to 2. So it's a two-dimensional distribution. Now, of course, I can do Metropolis Hastings, and I can have a two-dimensional proposal distribution. And of course, the higher dimensional the proposal distribution, the harder it becomes to have the proposal accepted, because it becomes difficult to propose things which are reasonable for all dimensions. Now imagine if we have R from 1 to 10,000 or R from 1 to 100,000. It just becomes increasingly difficult to propose reasonable things that then get accepted. So what we're going to do is we're going to, well, start with some R1 and R2 at the 0th iteration. Now, Gibbs sampling is a type of Markov chain Monte Carlo, so we have to start somewhere and then subsequently iterate. So the first thing we're going to do is we're going to sample R1 conditioned on our initial sample from the distribution of R2. So the coinciding density here would be P of R1, R2 naught. Now, we've initiated R1 and R2, but we don't actually need R1 naught, because what we're then going to do is we're going to sample R2 given the R1 that we have just sampled here, and that's going to be sampled from the following distribution. This distribution is P of R2 given the R1 that we have just proposed. And after these two steps, we now have a R1 to 2, whoops, no line here, R1 to 2 after first iteration. So we started off with a R1, 2 not. After one Gibbs step, or one Gibbs iteration, I should say, we obtain an R1, 2. And then afterwards, we can keep on iterating in order to obtain other pairs, R1, 2, 2, R1, 2, 3, and so on and so forth. Now, the idea is that, of course, this is not limited to a two-dimensional distribution. You can do this for an arbitrary m-dimensional distribution. So the algorithm for Gibbs sampling, written a little bit more generally, is written as follows. You start with R, one to m0, in addition to every single one of your conditional distributions. That is really the key to Gibbs sampling, is that you really must have access to all of these guys. We'll discuss in specific example how we go about obtaining them, and it sort of will highlight the importance of starting with conjugate priors. But the idea, therefore, is that we do the following. So for each m from 1 to m, you're going to sample Rm, let's call it Rm nu, drawn from the distribution R minus m, m, and here this is conditioning on the most recent R minus m. And then afterwards, you do sort of one Gibbs step for each one of your m variables, updating them one at a time. And then subsequently, this provides you sort of the samples for one Gibbs iteration. So somebody may ask, does the order of the variables in which I sample make a difference? It does not. This again is a Markov chain Monte Carlo sampler. You know, it has certain requirements, ergodicity, feasibility, and so on and so forth. Those are not violated by swapping the order of the variables in which from which I draw my sample. So for example, I can draw R1 given, let's suppose we have a three-dimensional distribution, R2 to 3, and this will be drawn from a distribution that depends on R2 to 3. Then I subsequently sample R2 given this R1 nu. The R3 has still not been updated, so this is pi of R1, R3, and subsequently I sample R3 from 1 R2. Both R1 and R2 are now new, so we have, or have been updated, so now we have pi of R1, R2. Now I could repeat this process and choose to sample the R2 first. So in principle, this may look something like this, where I have R2, and then R1, R3, and this would be R1, R3, and so forth. And then if I can choose to sample R1, R3 in that order, and so on and so forth. What I can also do when I do Gibbs sampling is that I can choose to sample R1, R2, R3 at my first iteration, and I can subsequently randomize the order of the variables. These are called random sweep Gibbs samplers. They can be useful in helping with sort of the mixing properties of the Markov chain, which we'll talk about shortly. But in any case, bottom line is that the order itself is not absolutely critical. So now we can ask ourselves the question, where was the acceptance ratio in all this? I mean, we're talking about Gibbs sampling as being an example of Markov chain Monte Carlo, but where's the acceptance ratio? It doesn't feel like Metropolis Hastings. In fact, we can think of Gibbs sampling as a special case of Metropolis Hastings where the acceptance ratio is 1. Now, if we think a little bit carefully, we've done something very special. In order to be able to draw R1, R2, R3 in a way that guarantees that the acceptance ratio is 1, then that suggests that our proposal distributions were selected in a very particular way to justify this algorithm here. So maybe in a nutshell, very briefly, I want to explain why the Gibbs sampling works. Why Gibbs works, and in particular, why the acceptance ratio is 1. So let's go ahead and write down what the proposal distribution is for Gibbs. We haven't made it explicit in the algorithm that we showed earlier, but in principle we can choose to make it explicit. Let me go ahead and write it, and then let's go ahead and see if we agree with what I've written. Now there's a lot of subscripts and superscripts here, so I'm looking down a little bit to make sure I don't mess anything up. R minus M proposed. And sorry, I ran out of space here a little bit. Let me write this a little bit more neatly here. So we have R old minus M. Okay, so this is the proposal distribution for the mth variable and everything which is not the mth variable. What does this proposal distribution look like? Well, if we follow a Gibbs sort of rules, the old and the proposed for the minus m are the same. That's why we have a delta function saying that R old for all of the minus m variables is the same as R proposed for those same variables. The only thing that is updated is the mth variable for which we propose according to the following conditional distribution. Again, remember this is P of Rm proposed, condition on Rm old. So in other words, R old stays the same, and P of Rm proposed is proposed according to the following conditional. That's what we did. We didn't write down this proposal distribution explicitly, but ultimately this is what we did. Now, if I can show that selecting this proposal distribution, my acceptance ratio is 1, then I will have justified the Gibbs sampling algorithm. So let's go ahead and write down what the acceptance ratio is for this proposal distribution. This again will be a little bit notation heavy, but we have pi of Rm proposed, R minus M proposed, divided by pi of Rm old, R minus M old. And now I have to multiply by the ratio of the proposal distributions, right? So this is the ratio of the targets, and now I have to multiply by the ratio of the proposals. So I have R subscript M proposed, R minus M proposed, and that's Rm old, R minus M old, divided by Q, Rm old, R minus M old, Rm proposed, R minus M proposed. Great. That's the acceptance ratio. In other words, the ratio of the targets multiplied by the ratio of the proposal distributions. So let's go ahead and write down the targets and the proposal very explicitly. And I apologize again, this is a little bit notation heavy. So I have pi m R sub m proposed Rm proposed multiplied by pi minus m, R minus m proposed, divided by pi m, R minus m old, Rm old, pi minus m, R old minus m. Okay, so let's just talk about what we've done. I've just taken what I have in the numerator here, and I've broken it down as the probability of R minus m multiplied by R of m conditioned on R minus m. This should be minus m. So this is pi of R minus m multiplied by pi of Rm conditioned on R minus m. And the same thing for the denominator, except that the proposed is substituted for old. So now I have the ratio of the proposal distribution. So that's going to be the expression that we wrote down earlier, which is the product of a conditional and a delta function, because the minus m old are equivalent to the proposed. So we have Rm old multiplied by delta function R minus m proposed, and in the argument of the delta function we have R old minus m close bracket. And then finally in denominator we have pi of R minus m old m Rm proposed R old, and then we have R minus m proposed. Good. So what do we notice happens here? First of all, R minus m old is the same as R minus m proposed. That's precisely what these delta functions are telling us. So this and that cancel out, and they give me 1. Now what about here? I have Rm proposed, and here I have Rm proposed. Here I have R minus m proposed minus R minus m old. But remember, old for the minus m variable is the same as proposed. So this cancels out with that. And of course, by exactly the same argument, this cancels out with that. So we end up with an acceptance ratio of 1. So what's the moral of the story? The moral of the story is that if I happen to select a proposal distribution which has precisely this form for the mth variable, in other words, it's drawn from the conditional distribution, keeping everything I'm conditioning on constant, then I can guarantee that the acceptance ratio is 1, justifying the Gibbs sampling algorithm. So we've done enough theory. Now at this point, let's consider an example. This is an example for a conditionally conjugate normal gamma model. So in this particular case, we're going to assume that the precision is drawn from a gamma distribution with 2 hyperparameters for the scale and the shape. The mean itself is drawn from a normal distribution with a mean xi and a precision psi. And finally, the data conditioned on mu and tau is simply drawn from a normal distribution with some mean mu and some precision tau. The data are assumed to be IID, right? So each one of our n's here are independent. So our likelihood is simply going to be a product of these Gaussians. Now the question is, what do I want to learn from this? Well, there's not much to this problem. So, if my likelihood is expressed in terms of 2 parameter mu and tau, then my goal is to learn those 2 parameters, which is why I've placed priors on both mu and tau. And just to reiterate something simple, but this here's what we would, or this line here is the likelihood, and it's also what would be called a generative model, because given a mu and a tau, this is how you generate the data. These two here obviously are priors on mu and on tau. Okay, so Gibbs sampling says that I would need to construct a p of mu conditioned on tau in the data, and I would also need to construct a p of tau conditioned on mu and the data. The only question is, how do I go about obtaining both of these conditional distributions? So, to be clear, in Gibbs sampling, I would start with mu 0, tau 0. Those are my variables that I wish to sample. And then I would iterate the following. Mu conditioned on tau, drawn from p of mu, tau in the data. I know I'm writing the density here, but tau, as opposed to the probability distribution, but tau given mu, p of tau mu, w1 to n. So this would give me a sample. Each one of these Gibbs steps would give me a sample of mu and tau, and I subsequently go ahead and I iterate in order to obtain subsequent samples of mu and tau. And again, if I want to be super clear, this would be j, this would be nu, and this would be nu, and this would also be nu. So I would take this mu and I would put it in here. This would be the one from sort of the, maybe instead of calling it j, I can call it old. This would be the one from the previous iteration. Okay, so the question is, or the question remains, how do I find this guy? It's not too bad, because if we go ahead and we consider the fact that we have a likelihood expressed in terms of mu and tau, really the only way for me to take the mu and to push it to the left-hand side of the conditional is to multiply by the prior on mu. Now, the proportionality constant, again, is something which is going to be independent of mu. And in fact, in this particular case, will only depend on the data. It'll be the evidence. So this is how I go about calculating my conditional on mu. The question is, what is this distribution? Well, p of mu is a Gaussian. The likelihood, to be very precise, is another product of Gaussians. Again, this is a Gaussian. So when I multiply a Gaussian by product of Gaussians, I simply get another Gaussian. So what I would have to do is multiplying this by this, I sort of recomplete the squares and make it look like a Gaussian in terms of mu. And again, what about all these other terms? I don't care because they don't depend on mu. They're just going to be constants outside. In principle, I can take my Gaussian, I can renormalize it, and obtain those factors if I wish to, but I don't need them. So if I do the math correctly, I take this product of Gaussians, I multiply with this one here, then I should be able to get a mean, or p of mu, conditioned on tau, and w1 to n, is going to be a normal in terms of mu. And the mean, if I do my math correctly, will be tau will be the following. So psi times xi plus the precision multiplied by the sum of the data divided by psi plus tau n. And the precision will be psi plus tau n. So that's how I obtain my first conditional. Now if we notice The reason it takes a nice form is because that prior was conditionally conjugate to the likelihood that I had in terms of the variable mu. So since my prior was Gaussian, and my likelihood happened to be Gaussian as well, then multiplying the two, I obtained another Gaussian in mu. And that was guaranteed, again, simply because I selected a conditionally conjugate prior. Now we can ask the question, what about P of tau given mu and W1 to n? And that is going to be a very similar thing. That's going to be proportional to the likelihood, which at this point I can go ahead and write down as the product of my Gaussians multiplied by my P of tau. Now remember, my P of tau is gamma, and we've gone through this example before where my likelihood has gamma-like behavior when it comes to the precision, right? So the normalization has a 1 over tau term, and the exponential is e to the minus tau multiplied by something. So this entire thing ends up being precisely equal, if I were to combine the terms, to a gamma distribution on tau with renormalized parameters. Just like this was a normal with renormalized parameters, mu tilde and, well, let's say 1 over tau tilde. And what are these renormalized parameters? Alpha tilde and beta tilde. Alpha tilde turns out to be alpha plus n over 2. And beta tilde turns out to be 1 over 1 plus beta plus 1/2 sum n from 1 to n wn minus mu squared. So this was for the very simple example of a conditionally conjugate sort of mean and precision pair. What about if we do Gibbs sampling on a sum of Gaussians? It's a slightly more difficult example. I'll tell you exactly what it is. And by, another word for sum could be a mixture of Gaussian. So now let's go ahead and write down our forward model. So we have a prior on the precision, alpha beta. Then we were going to have a prior on the mean for the first Gaussian. We're going to assume we have a sum of two Gaussians in our likelihood. So the normal is xi, and the precision is psi. We have another prior on the second mean. Now we're going to have a latent variable, and that latent variable will tell us for the data which one of the two Gaussians I'm drawing data from. That's going to be drawn from a categorical with two components and two weights, pi1, pi2, and of course pi1 plus pi2 is equal to 1. And finally we have our data given Sn, mu 1 to 2, and tau, which itself is drawn from a normal centered at mu sub Sn and 1 over tau. Okay, so let's say a word or two about this example, because it's already considerably more complicated than the previous example we've looked at. These two lines are our generative model. So if I want to synthesize or generate the data, I first have to say, okay, for this data point, and all the data are going to be IID. So for this data point, I draw my data from one of the two Gaussians with some weight. Maybe one Gaussian is 80% more likely than the other. And those weights are given in this problem. There's no prior on them, so they're known. They're just numbers. And once I have selected which of these I'm going to pick, then I draw my data from that particular normal, which is centered at either Sn is equal to 1 or Sn is equal to 2, depending on which of the two options were selected, which of the two Gaussian or mixture components were selected. So these 2 lines here are our generative model. These 3 lines here are the prior. Now, again, there could be more lines in the prior if I assume, for example, that the mixture weights themselves are unknown. But for now, we're assuming that these are known. So what is there to learn? Well, there's a couple of ways of proceeding with this problem. We could try to learn the precision and the 2 means of the Gaussian. And this problem, again, is a little bit simple because it says that the precision for each one of the Gaussians is the same. You don't have a precision which is different for both mixture components. But we could, in principle, try to learn the mean of both mixture components as well as their one precision. But that would require that we marginalize over these latent variables, these S's. We're not there yet, so what we're going to do here is basically sample or try to learn the mu1 to 2, the tau, and the S1 to n. So this is really kind of, whoops, not sure what happened, but this is the mu1 to 2, the tau, and the S1 to n. This is really kind of the first example where we are genuinely learning a very large number of parameters. So if we have 100,000 data points, we literally need to learn 100,000 plus 3 parameters. That's a large number of parameters to learn. So we are going to do Gibbs sampling. We can try to come up with a 100,000 plus 3 dimensional proposal distribution and do Metropolis Hastings, and chances are it will not work very efficiently unless the proposal distribution is very, very finely tuned. So a better way to do this is to do Gibbs sampling. So how are we going to do it? Well, we are going to generate a tau nu from P of tau given mu1 to 2 old, S1 to n old, and the data. Now, after this Gibbs step, we will generate a mu1 nu from P of mu1 given mu2 old, tau nu, because now that's just been updated, S1 to n old, and W1 to n, our data, which are just numbers. And then, of course, we do the same thing for mu2, for P of mu2, given now mu1 old, mu1 nu, which has just been updated, tau nu, S1 to n old, and Wn. And finally, we have to do this for n from 1 to n, S1, or Sn, let's call it nu, from P of Sn, whoops, given tau nu, mu1 to 2 nu, S1 to n minus 1 nu. We assume that we've updated all of the previous s's. Sn plus 1 to big N old, as well as, of course, the data itself. So, we basically have to do this, then that, then that, then that. 4 steps form one Gibbs iteration, and then after one Gibbs iteration, we obtain a tau nu, mu1 to 2 nu, S1 to n nu. That's one sample, and then we can iterate again. So the real question then becomes, how do I obtain this, 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 and that? So let's go ahead and show how we obtain each of these distributions very briefly. So P of tau, given S1 to n old, mu1 to 2 old, And the data is once again going to be obtained from the data. So the data is going to be Wn Sn mu sub Sn tau close bracket times P of tau. Now, there's one thing that's very important here. At every iteration, I know, or I have, an instantaneous realization or a value for Sn. So when I sample P of Sn, or when I sample tau, I know at the previous iteration what the S sub n was for each one of my data, Wn. So this is simply again going to be a product of Gaussians. It will not be, and this is very important, it will not be a product of a sum of Gaussians. That would be intractable. It's genuinely a product of Gaussians because I'm conditioning on Sn. P of tau is a gamma, so of course, just as my example before, I expect this to be a gamma with some renormalized parameters, alpha and beta, which I can easily calculate in the same way that I have previously. So that was P of tau. What about P of mu1 given mu2 tau S1 to n and Wn? What is that proportional to? Same thing, but we can be a little bit more precise here. We're going to have the data. Let's go ahead and write it down. P of Wn conditioned on Sn, mu sub Sn, and tau, that's my likelihood, multiplied by P of mu1. Now, this likelihood here, again, every data, the data are all IID, so they're coming from either one mixture component or the second mixture component. I can technically split this up into two products. The products for which Sn is equal to 1 and the products for which Sn is equal to 2. In other words, the data that came from the first mixture and the data that came from the second mixture. If we notice here, we have some terms that depend only on mu1 and other terms that depend only on mu2. But if my goal is to construct a conditional posterior on mu1, then I don't care about the mu2 dependencies. In fact, they're just constants. So in principle, I can rewrite this as a product, the product with the understanding that Sn must be 1 here, of P of Wn Sn, or let's call it Sn equals 1, mu sub 1, tau, P of mu1. And in this proportionality, I've taken out all the terms in the product where the Sn was equal to 2. Once I do this, then I notice that this is a product of Gaussians, fewer Gaussians, but still Gaussians. And this here's another Gaussian, and so I can go ahead and construct my distribution as mu. And then I'm going to have a mu tilde and 1 over tau tilde. Basically, I just have a restricted product of only those terms where Sn is equal to 1. Again, if I choose not to do this, that's perfectly fine, but I'm going to be collecting a bunch of constants, which are going to cancel out, or I can figure out by renormalizing my Gaussian. But all the terms that depend on mu2 in this prefactor here will cancel out. Okay, now comes the big one, which is how do I go about determining P of Sn conditioned on S minus n tau mu1 to 2 and W1 to n? What is that equal to? Well, let's go ahead and rewrite this as my product. This is going to be, or again, proportional to, P of Wn conditioned on Sn mu 1 to 2 and tau multiplied by P of Sn. Now, there's an important thing that we should say. This likelihood we break down as a product, and only one of those terms is going to have a n which coincides with this one here. Right? So in principle, this is maybe bad notation here. Maybe I could call this m. I call this m. So only one term in the sum will have a Sn for which n is equal to m, and this will be mu sub Sm tau P of Sm. What is this guy going to be equal to? Well, this will be a Gaussian, a normal Wn centered on mu sub Sm with precision 1 over tau. And what is this going to be equal to? It's going to be a categorical. And that categorical will have two terms. Pi 1 to 2. And it's equal to Sm is equal to 1 if I happen to draw from that portion of the categorical with weight pi 1, and otherwise Sm is equal to 2. What happens when I multiply this normal by this categorical? Well, what I get, if I go back to the definition of the categorical, sort of as the sum of two delta functions, remember the categorical density is really a discrete density that is the sum of two delta functions. It's going to be a categorical, and let's write it down as pi 1 multiplied by my normal Wn mu sub S1 1 over tau, and then the other argument will be pi 2, and then another normal Wn mu sub S2 1 over tau close bracket. Now, the only thing is that this and that have to sum to 1, so I need to renormalize the arguments of the categorical. So if I take this and that, and I take their sum and I call it C, then I can divide this by C, divide that by C, and that becomes my new conditional posterior for Sm. So it's another plain old categorical. It turns out that without knowing it or without specifying it explicitly, we happen to select, by virtue of having a categorical, we have something which, a posterior, which is still categorical, and therefore was conjugate. So this distribution is now straightforward to sample from. So putting it all together, Gibbs sampling for the mixture of Gaussians requires a P of tau which we already said was gamma, so we know how to sample from that. We have a P of mu for each one of our mu, either 1 or 2, which we said is normal, and we know how to sample from that. And finally, for each one of our n's, for n from 1 to n, we have a categorical distribution, which we also know how to sample from. So in the end, each one of these are our, n plus, and here we have 2, so n plus 3 steps, and then we subsequently iterate. So hopefully what I've convinced you of is that sampling multidimensional posteriors is possible. You can achieve this through Gibbs sampling if you choose to. And you can choose to do it if you can somehow easily construct these conditional posteriors. Now, maybe there's one last thing that I can mention about Metropolis Hastings within Gibbs. And the idea here is that if you have to sample some variable R1, let's say, maybe doing this step is possible because you can construct a conditionally conjugate posterior here. But maybe by the time you get to R2, it becomes difficult. So this would be new. This would be old. This now is new. This is old. This is new. So these guys are old. This guy is new. This guy is old. And, and so forth for R3. Maybe by the time we get to this step, I don't know how to construct this conditionally conjugate posterior. But guess what? I can potentially do Metropolis Hastings for that step. Why is that? I'm still drawing samples from a one-dimensional distribution. I'm drawing samples for R2. So even if I cannot construct a conditionally conjugate posterior or a analytic posterior from which to sample from or an analytic target distribution, I should say, from which I can sample from for each one of these cases, I may be able to do it for some intermediate case, for one step where I may have to invoke Metropolis Hastings. And doing Metropolis Hastings for just one variable at a time, and maybe each one or maybe two of the three steps, for example, but doing this one-dimensional Metropolis Hastings will turn out to be a lot better than attempting a multi-dimensional Metropolis Hastings where technically your acceptance ratio can drop considerably. So I think we've sort of summarized the basic ideas behind Markov chain Monte Carlo with Gibbs sampling. And what we will be looking at next will be methods by which to sort of determine how to clean up our MCMC samples, how to remove sort of initial samples that may be very biased and dependent on the initial conditions, and how to go about looking at mixing properties of our chain. So with that, thank you.